Hi there and welcome from Ventura, California to today's webinar, third in a series of 3 webinars that make up Unmanned Systems Week. Today is Unmanned Solutions and Applications Day, sponsored by Novotel and Inside GNSS and hosted by WebAttract, the leaders in thought leadership webinars. My name is Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they present case studies of specific unmanned systems and their applications. You'll also have an opportunity to have your questions answered at midpoint and at the end of the presentation during the Ask the Experts panel session with all 3 of our panelists today. Now, we've invited a diverse audience spanning 34 countries and 29 states and provinces, representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. Now, before we get started, I would like to invite Glenn Gibbons, editor and publisher of Inside GNSS, to take a moment to welcome you and introduce Mark Petavello, who will be moderating the main portion of today's webinar. So over to you, Glenn.
Thanks, Lori. And on behalf of Inside GNSS magazine, our sponsor Novotel, and our panel of experts, I welcome you to this final installment in our 3-part web seminar series on unmanned systems. It's been quite a week, with our previous webinars providing overviews on unmanned systems applications and operational requirements, on GNSS positioning options, and on integrated navigation and positioning methods for autonomous vehicles. Today, along with our moderator, 3 speakers will describe several sensor and system designs and their use on unmanned air, ground, and marine platforms. We will hear from 3 panelists about how unmanned systems can be used for dull, dirty, and dangerous applications such as mining, environmental monitoring, mapping, bathymetry, farming, and security and surveillance. So please sit back and get ready to enjoy today's webinar. And thank you for joining us. Now it's time to introduce our moderator for today, Dr. Mark Petavello. Mark is a professor in the Department of Geomatics Engineering at the University of Calgary in Alberta, Canada. He is also a contributing editor for Inside GNSS magazine, where he coordinates the column GNSS Solutions. Mark has been actively involved in many aspects of positioning and navigation since 1997, including GNSS algorithm development, inertial navigation, sensor integration, and software development. Mark, it's great to have you with us again. Welcome.
Great, thanks a lot, Glenn. And I would also like to extend my welcome to everybody out in the audience today. We have a very globally distributed panel of experts today, coming to you from Canada, US, and Europe. And hopefully by the end of it, you'll learn a little bit about some of the applications that you can use unmanned systems for and the benefits that go along with those systems compared to traditional techniques. Before we get going, we'll start with our first poll question, and I'll turn it over to Lori to take care of that for us.
All right, thank you, Mark. And folks, coming up on your screen is that first poll question. And in this case, while you can select all that apply, we're asking on your honor system, please select your top 2. So what are your top 2 applications that you are interested in using unmanned systems for? Mapping and surveying, precision agriculture, mining, environmental monitoring, security and surveillance. What are your top 2? Looks like we have 70% saying mapping and surveying, 18% precision agriculture, 10% mining, 36% environmental monitoring, and 51% security and surveillance. So, Mark, any thoughts on these results?
Again, as per some of the previous webinars this week, there's quite a diverse range of applications. It's kind of nice to see near and dear to my heart, mapping and surveying right at the top. And you'll definitely see some discussions about applications about that today. So without further ado, as was mentioned, this is the 3rd of an installment of 3 webinars this week. And we'll start off with a quick review from Monday. Monday we talked about GNSS-only systems, looking at the applications and some of the metrics, the positioning requirements in terms of GNSS only, the role of multiple systems, and of course the issue of interference has to come up in that discussion, and then the accuracy requirements depending on your application, be it standalone or differential. And there was also some discussions about aerial and marine systems, again with GNSS only navigation sensors as the navigating system. On Wednesday, we took a slightly different approach. We looked more at the specifics of the integration, but not just with GNSS, also including inertial and possibly some other sensors. So considered several different ones, LiDAR, cameras, odometers, and many others, and how to integrate all those together in various fashions and the pros and cons of doing so. And then wrapped up on Wednesday with a very nice discussion about the methods that you need to or the steps you need to go through in order to actually develop a practical system, starting from the equipment and your algorithms all the way up to your final deliverable. And today is, as Glenn mentioned, all about the applications. I won't spend too much time. I think Glenn did a very good job of introducing it, but really looking at some of the applications and the benefits of these applications to various companies as they are currently being deployed. So without further ado, we will start off with our first panelist, who is Mr. Jeff Fagerman. Jeff studied surveying and photogrammetry from Ferris State and Purdue, respectively, and has a background in advanced imaging in many other areas as well. He has 14 years of experience at Intergraph in photogrammetry development. In 1999, he formed Fagerman Technologies, where he provided photogrammetry services and consulting. And later on in 2010, he started LiDAR USA Solutions with his son Daniel. His most recent activity is in regards to miniaturization of LiDAR solutions, and I think you'll see how successful he has been in that particular endeavor as he starts us off today talking about some of the mobile mapping systems that they've been working on. So Jeff, I turn it over to you.
Thank you, Mark. I want to thank everybody for joining this presentation, and especially our organizers and Mark, our moderator, and Novotel for sponsoring this. And today my session will focus on mobile mapping applications from the ground, from water, and from low-altitude aerial platforms, with our primary emphasis on LiDAR scanning. Even though I'm a photogrammetrist, I do both photogrammetry and the LiDAR. This series is going to be geared more towards unmanned vehicles, even though our equipment at LiDAR USA is really platform independent. It's largely true of the applications that we service as well. I want to begin by looking at what is required to make a mobile mapping mission successful. In short, every mission is completely dependent upon knowing where the instruments are, where they're looking, and when. Basically, position, orientation, and timing. For UAV implementation, of course, size and weight are just about as important. If we can't lift it up, if we can't get it to where it needs to be, we have a problem. So size and weight are very important there, but they're also important just in the platform itself. We do a lot of traveling with our instruments. When you travel by air to get from one job to the next, it's nice if you can carry it with you on the plane as overhead luggage. So size and weight are also important in that sense. The system can't be exorbitantly expensive, and it's got to be able to work when you expect it to work, and it's got to be able to handle the luggage carriers in the airport, and it's got to be able to be safe for the environment and friendly to use. The applications that we serve, initially I'm a geomatics person as well, a surveyor and a photogrammetrist, but the applications that are available for mobile mapping, LiDAR mapping, and imaging is just extremely diverse, and I've listed I think 12 or 13 right here. The accident scene reconstruction has nothing to do with surveying. It was our very first project we did, was for accident scene reconstruction. Disaster relief, the Katrina type stuff, the Sandy, all those kind of things, Haiti. Mapping, very, very rapid mapping of what happened and getting that documented. Surveying, of course, engineering, GIS, forestry is huge, agriculture is huge. Each one of these areas is a very, very, very big market, and they each have their own little twist involved in them. Tourism at the bottom was something I wouldn't have dreamed of either, but there's a lot of people who want to map an area to draw people into it so they can go onto the web, look at it, kind of like a simulation or a game, but they're bringing the customers to them through scanning. This system right here, we call our system the ScanLook, and Snoopy is our new incarnation of it, and it's real small. You can see we have a Velodyne scanner, so I guess to begin with, we need to know what parts are important parts on a mobile mapping system. Obviously, the INS is probably first and foremost the most important thing. If we don't know where we're at, where we're looking, what time it is, it doesn't matter. Our data has no value. So inertial navigation system is most important, and we have here the Novatel system mounted here with the STIM 300 from Sensona inside. And then we have the antenna that goes along with it. We also have a multitude of scanners that we use. This is mounted with the Velodyne scanner right here. A very nice little scanner. And then we have our imaging system to the rear of it here. And it's all mounted on an SUV with just simple vacuum cups to hold it in place. And this all collapses down and fits in an overhead luggage for air travel. The key is it needs to be small. It has to be small, but it also has to be able to do the job. It has to be able to be deployed on whatever vehicle we're working on very, very rapidly, and it has to be easy to move from one site to the next, to the next, to the next. This platform here can be hooked onto a car, a truck, a boat, a rail, you know, a multitude of things, and you'll see even onto a UAV here in just a little bit. So here's another system that we built. It's basically the same thing, only the thing has changed. You see we still have the antenna and the scanner both here, but we have a different IMU. It's a higher quality IMU. It's ITAR restricted, just a very robust system. And we have the Faro scanner added on as well. So we have two different types of recording instruments. Before we had the Velodyne and the video. Now we have the Velodyne scanner and the Faro scanner, both serving very important parts of our mapping and very different at the same time. The Velodyne, for those who don't know, shoots out 32 lasers in a 40-degree field of view, collecting 700,000 points a second. The Faro collects at 976,000 points a second, but it's a single-line scanner, but it's very, very, very accurate, an order of magnitude more accurate. Another part here is that the Faro is detachable, and you can do scanning on a tripod. It's bigger than the Velodyne, but it's still relatively small and light. Still can be part of a UAV implementation. This particular system here is geared more towards a being able to handle longer outages. I think this actually is an FSAS IMU. What system I really was referring to was the LCI 100, which is ITAR restricted. Subway scanning, obviously we have no GPS. Setup time is absolutely crucial. We have 25, 30 guys standing around watching, and we need to be able to set our system up very rapidly. This is usually done between midnight and 1 a.m., and we have a very small window of time in which we have to do our scanning. So setup time is extremely crucial, and being able to function without GPS for extended periods of time is very crucial. And in the end, we have to deliver a very accurate point cloud, and basically failure is unacceptable. Each time they close something down, it costs a lot of money. So moving on, I want to show here is something that's going to just, you know, in the U.S. it's not really totally legal, neither illegal to fly UAV. So we just kind of shy away from that by sticking with a helicopter implementation. In this case here, we have the little Snoopy system we saw in the first one sticking out the side of this helicopter. You can see the antenna and the Velodyne scanner, and that's pretty much all you can see. But the point is here, this was a very quick and simple mounting system. It was secure. It's completely legal. It's very cost effective. It doesn't cost much to rent a helicopter, and we can take it to virtually anywhere because there's helicopters all over the place. But key to being able to do this is it has to be of the right size and right cost, and it has to be able to do the job. Now, obviously, if we can do it from a helicopter, which has a lot of high vibration, we can also do it from a UAV. Okay, here is that same thing. Just a few minutes later, we were out over, you see, a very, very wet area with lots and lots of islands. The unit here weighs under 10 pounds, not including the mounting bracket. Can't float in midair. And we're scanning just with the Velodyne, which is a 15, 20 millimeter scanner with a range of about 80 meters. Now, the cables you see here are running into the helicopter so that I can actually monitor the system from a laptop, and we provide power for it. Obviously, if we're on a UAV, we wouldn't have those cables. It'd all be localized to the platform itself. Okay, here is some of the results from the scanning that we did on this particular job. We were scanning a little island, and this is a Google Earth image in the lower right corner, and you can see the waterways and the vegetation, and there's not a lot of vegetation. It's really very flat, and all the vegetation is only 6 to 12 inches high. But here is the LiDAR data processed into a surface model, and you can see the waterways. You see the little crook here, it matches the Google Earth image there, and this is very, very accurately mapping this particular area. So we can do watershed analysis, and we can do change detection from one session to the next over a period of time. So accuracy is important to us, not just the relative accuracy of the point cloud itself, but the absolute accuracy. So we have to be able to come back to this thing a year later and register back up again. So for us, we don't talk in terms of meter or decimeter. We're typically talking in terms of a centimeter, and no more than 2 or 3 centimeters. That'd be too much of a change for us. Here is another implementation. This is on a gyroplane. The same system, slightly modified. Again, you see we use the Velodyne again, a different INS, same antenna. We just mounted this on the nose of a gyroplane. These reminds me of the George Jetson vehicle. Very small, no payload limitation as far as we're concerned. I mean, it can lift, 2 people and several hundred pounds of equipment. So unlike a UAV, we don't have to worry about miniaturizing, but we still have to make it small because there's not a lot of room in one of these gyros. So it still had to be small and light, and we had to make it so it's simple to mount. And again, we use the vacuum cups on here. The scanner has to have a good viewing angle of what's being scanned. The antenna has to have a clear view of the sky. Those are all kinds of issues that when we first set up, it's a little bit tricky. But they're all very, very important. It looks trivial in the end, but it took a little bit of thinking, an hour or 2 hours to figure it out. But the helicopter implementation and the gyroplane implementation, each time we keep making the system a little smaller, a little more portable, and getting us one more step closer to a UAV implementation. It's not just the size that we're worried about as well. It's vibrations and being able to securely and reliably get the data out that we need, because we need that high accuracy data. And along with that then is we need a good GPS system, recording at least L1 and L2, and the IMU, making the whole INS system, the synergy of the GPS and the IMU working together. So here's another system again. We still would refer to this as our Snoopy system. It's just using a different INS. We can keep reconfiguring this. As you see, now we don't have the video on here. We don't have the Faro on here. Actually, we have a different set of cups on here to mount. Just a different INS. A slightly larger INS. It's more expensive. A very, very durable system. Very good at GPS outages. Yet the system is able to remain small and compact and accurate, which is very important for every job we do. We seem to start off wanting 10 centimeter accuracy. In the end, our clients are always pushing the limit. They would like, can you get down to the centimeter level? They can even push to get down below sub-centimeter level, depending on the project. So oftentimes, it's very important to have a runtime feedback as to what's really happening with the satellite constellation, with the IMU, what's really going on. So we need to have some feedback, especially in the mobile mapping in the urban canyon areas. You're ducking underneath trees, underneath bridges, behind tall buildings. Some of these things aren't, you can't do anything about. You go underneath the bridge, nothing you can do about it. Of course, you're going to lose everything for an instant. That's where our IMU kicks in and takes us. It's not like doing a strictly RTK solution where you duck behind something and you lose your RTK and your accuracy drops. Our IMU kicks in with the software, and we're able to maintain all of our accuracy basically for short periods of time. Short periods of time being anywhere from 10 seconds to 60 seconds, and even more depending on the INS you have selected, and all the different sensors you can have. As well, we can have wheel meters attached to the system to continue to give us linear input. So if we drop GPS, we have additional sensors helping to guide our positioning and orientation. Now, obviously, the orientation primarily comes from the IMU, but key here is to be able to see that I have suitable satellites, to see that my DOP, my dilution of parameters, are suitable for mapping, and you have to ask, well, what if they aren't? What am I supposed to do? Sometimes there's nothing you can do. If you're on a railway and you're going through a jungle, sorry, you can't get rid of the jungle. It's just going to stay there. And you just have to know that you have to come back and supplement the data with control, or you just have to live with the results. Or alternatively, you could upgrade your sensor to a probably a better IMU or INAS system that's less susceptible to GPS outage. Okay, just a real quick slide here. We always do post-processing generally because we want the best results we can get, or our clients want the best results we can get. Part of that is we have to know what our lever arms are and our orientation is to each one of the different sensors, whether it's the Velodyne LiDAR sensor or the Faro or the video or thermal infrared or whatever sensor we have on there that needs to know where it is and where it's looking. We have to have a good bore sight. Also part of this, we have to have base station set at appropriate distances, recording at the right frequency, recording the proper bands and the satellite constellations we want to use. I mean, generally we recommend at least GPS and GLONASS in there. And the duration of the mission is also important in this because it'll affect some of the other things we do. And then again, the accuracy, it kind of gives us some idea what we can get to. So when we're processing, we could obviously use RTK solution because we get position and orientation in real time, and we could use that data. We generally don't use that because of the outages, and because we know if that was all we had, we would use that, but we know we can post-process and improve that significantly. So the post-processing steps, we can use PPP, post-process data. It's very good, but then to use that, you got to have like no GPS outages during the whole time you're there, and you've got to be have no GPS outages for at least an hour or more. We typically use post-process DGPS, which allows us then to do loosely coupled, tightly coupled, combined, smooth, forward, reverse solutions, and it pushes us towards achieving the best results that we can get, which is exactly what our clients want out of our data. And in the end, we're going to be mapping. We're going to be using a number of software products, and there's dozens of products out there. We typically would hand over a point cloud to our clients, and then they would bring it in, and they would do whether they do mapping, whether they're doing railway, right-of-way, whatever it is, they're going to have the appropriate product for that. Here's what we're all very, very, very familiar with: Google Street View and Google Earth. It'd be something like this. You know, without GNSS right now and without inertial, these products would be nowhere. I mean, it would be very, very localized if we had to use surveying or additional or traditional methods of getting our positioning. It would be much, much, much more localized. And here, just showing the effects of a couple of different sensors. This was scanned by one sensor and then another sensor, all scanned simultaneously, as you saw them earlier, and you can see the different effects, the shadowing one gets. One might have better shadow coverage, but not as accurate. So when we build a mobile mapping system, we have to know what our client is trying to achieve and supply the appropriate sensors for them. And here's another scan of a Disney area hotel entrance. You can see this was like 30 seconds of scanning, if it was even that long. We get a complete 3D point cloud, and using the appropriate software, we can go in there and measure the heights of the trees, the width of the parking lot, the height of the doorway, everything in the hotel entrance. Here's a residential area neighborhood scan. You can see this was done with a single line scanner, but this gives very accurate results. Just another thing we can do. And here are some of the suitable UAVs that we would typically use with our system. You know, a rotary, single helicopter, gas-powered, a multi-quadcopter. These two down here for carrying much heavier payloads. And this is a little device we had out just yesterday, a little helicopter flying around with our system on it. You know, it can go like 65 miles an hour, very low end, but it can do the job. So a lot of choices. You can spend little or a fortune. Here is just a quick results of a point cloud. This was scanned at 70 meters from a helicopter. You see the flight path, and you can see some of the results there. And this again is also some similar type data. This was the upper left image here is the results the raw point cloud with all the trees, and then the bottom is the ground surface only. You can see there's a deep ravine and a ravine running through here, and it's not nearly as evident in the top raw point cloud. So in the end, to do mobile mapping, we have to know location, location, location. That is what's primary of importance, is then our position, our orientation, and timing. That's a global solution. Doesn't work everywhere. We can't go indoors. Subways are difficult. Areas that don't have clear sky, and we have jamming. But we have alternate solutions for that, such systems as the Locata system, the cell towers, ultra-wideband, SLAM, and traditional surveying. That brings my presentation to a close. It's been a privilege to share this with you, and I'm going to turn it back over to Mark.
Great, thanks a lot, Jeff. Very informative, really cool applications, and definitely some really interesting images there. So hopefully our audience gained some useful information from that. We'll now head on to our second panelist before we get to our first Q&A session. So our second panelist is Blythe Gill, who has a background in environmental consulting and technology commercialization, and he currently leads the strategy and execution for EchoStream's remote sensing systems. He is also responsible for finding new applications for using robotic systems to collect important environmental data in an efficient and cost-effective way, while also eliminating any health and safety risks to his workers. And you'll see that in his presentation today. Blythe holds a bachelor's of science and a master's in business, entrepreneurship, and technology from the University of Waterloo. And Blythe's going to talk to us to start off today with an unmanned robotic systems for various applications. But first of all, he's going to start off with some of the systems and equipment that he uses to do so. So Blythe, I turn it over to you.
Thank you very much, Mark. Hi, everyone. It's a privilege to be part of this presentation. Thanks to Novotel and GNSS for this opportunity. It's pretty exciting. And to get straight to it, just going to talk about the bathymetric system that we have. So using an unmanned surface vessel for collecting high-quality bathymetric data. And I work for ClearPath Robotics. We've been around for about 5 years, and to develop this technology into a different area, we've developed a subsidiary called EchoStream, which has taken this technology to new areas. So that's part of my role, and I'll go over a little bit about the company quickly. ClearPath actually this weekend is celebrating its 5th anniversary, so we're a quite young company, and our mission is really to automate the world's dullest, dirtiest, and deadliest jobs. Expertise in unmanned vehicle systems, and last time I checked, we're about 40, but every day somebody new seems to be coming in, joining the team, so we're going pretty quickly. And we have robots across the planet with, I think, over 35 different countries right now. And so to break it down, really we provide products and services. As you can see, the Husky UGV is basically what has taken ClearPath to where it is now. It's really a rugged platform where you can equip any kind of sensor to do the kind of robotics automation that researchers and academics around the world need to do. So they get a really good out-of-the-box experience, and within an afternoon they're doing their research instead of getting a grad student to spend a few months developing their own platform to do this research with. We've recently launched the Grizzly, which is an ATV-sized platform. That's a lot more rugged. Also the Kingfisher USV, which is what I'll be talking about, as well as we do custom automation projects. The tractors you see there from Queen's University, used in mining applications. And so just what we do is kind of the opposite. We're platforms, and you can hook up any kind of sensor to our systems, where we can then develop autonomous software and do advanced mapping and navigation as well. Just a quick overview of some of the companies and clients we've worked with. We've developed quite the reputation, and Novotel has been a big supporter of us, and it's been great working with them to develop the solutions that our customers are looking for. So here's just a quick example of taking the Grizzly as a platform and then converting it for the needs of our clients with the appropriate sensors. Again, this is the custom automation example. So a lot of mining applications, agriculture, you name it. Customer comes to us and we'll help them build the appropriate solution to their need. But again, the application today that I wanted to talk about was collecting better bathymetric data, and it starts with better data collection methods. So really, there are a lot of need for bathymetric data. There's an issue though in terms of quality, how to collect the data, the speed, the cost, digitization of that data, and again, accuracy. Right now, the problems with conventional methods, and I'll show you a few pictures as we go through the presentation, but really it's often unsafe, it's very slow, it's expensive, it's non-repeatable, and it's, as we've realized, it's quite inaccurate the way things are done. So again, this is just an example of somebody crossing a river, moving body of water, trying to figure out where the bottom is, using a total station from shore. We have old examples of, how to collect bathymetry in a manual way. People out in a boat. I don't need to describe these pictures, but the old ways of doing things need to change, and that's where unmanned vehicles comes into play. So this is our Kingfisher system next to a well-known company. This was just last summer, that has a lot of experience doing bathymetry in stormwater management ponds. So they'll have a team of 2 out there, and this flotation device, I'm not even sure what it's called, but yeah, then it just comes down to the experience of the surveyor and how hard he or she wants to push on the rod to find where the bottom of the water body is and where the top of the sediment starts. So it's pretty inconsistent, unsafe. And so this is our system here. It's a one-person portable unmanned surface vessel. On the picture on the right describes basically every piece that comes with the kit. The base station, GPS, an operator control unit, or OCU as we call it. We have a single beam echo sounder and an MRU, which is inside the vessel. Again, we can hook up any kind of INS system to calibrate the system. And we also, for added accuracy, provide sound velocity probes, which correct the speed of sound in the water. And I'm going to pass it back to Mark quickly for the break. Thanks.
Great, thanks a lot, Blythe. And that leads us nicely into our first Q&A session. So if you haven't already done so, feel free to enter your questions into the panel on your screen, and we will do our best to address them either here or during the second Q&A at the end of the presentations in about half an hour from now. So we'll start off the first question to Jeff. And there's a couple people who have asked, specifically Octavian and Bryant, asked about the one of your slides mentioned how you don't necessarily need GNSS, and the question was, how do you go about initializing your system in that type of an application?
Well, that's a really good question. I mean, it's not without a lot of trickery, let's put it that way. We had to work with Novotel on that to find some ways, and I think we did some things that they weren't quite aware of. The key was we really had to use the LCI 100 to bring that about, to make that happen. But that's really about all I can really tell you. It was tricky, and it did require, to get the accuracy, we did have to use control points in the tunnels as well, because we would drift over time. But so control was absolutely required. But
Okay.
we went for hours without GPS.
Very impressive. Very good. Anybody have anything else to add if they have a similar application that they've experienced that? Chris or Blythe? No? If not, our next question will go to Chris. You haven't heard from Chris yet. He's coming up in a few minutes. But Chris, the question to you, and I'll ask everybody else to chime in as well, what do you consider the kind of minimum or perhaps average mission time for your particular platform?
For our particular platform, we specialize in long endurances. So we generally offer 6 hours endurance because we're flying long distances and we're doing some considerably tough challenges in some difficult environments. And if we are pushed and we're prepared to trade a little bit of payload, because we certainly have more payload than Jeff's platforms he was talking about earlier, we can actually push the system out to 10 hours. And that's one of the strengths. But we are, in reality, looking at a different part of the market because, to a certain extent, we're thinking about taking on the manned platforms and some of the manned platform applications.
Very good. Blythe?
So the typical mission lasts on average about 2 hours per battery, but with our system, they're easily swappable in and out, so we can spend 8 hours on site, or we can be at a stormwater pond where basically what would take half a day, you put the boat in and 20 minutes later you're done what you need to do. So it really just depends on the area and the body of water that needs to be surveyed.
Okay, very good. And Jeff?
With our applications, it ranges anywhere from 10-minute scan to literally 8, 10, 12, 14 hours. We can go as long as the human can go. We don't have no problem with power, and we have no problem with data storage. You can store a week's worth of data if you wanted to, but generally, a working day.
Okay, very nice. So quite the range there from a few minutes to many, many hours. Very impressive in every respect. The next question will go to Blythe. And again, I will open this up to everybody else if they're interested in contributing. What are the challenges, or what would be the challenges with making your system autonomous versus just unmanned?
Wow. Where to start on that one? Well, really, if you think about any kind of vehicle or any system that's autonomous, it's like a person. You have lots of sensors, and they're out there collecting data, and you have to interpret them and then act accordingly. So there has to be quite a bit of expertise in the sensor itself and what that actually means to the vehicle, and how to really program that vehicle to then interpret that information and act accordingly. So it can be as basic as waypoint navigation, where the vehicle understands where it is and where it would where you would like to send it to by just basically points on a map, to, well, this area is shallower, the sonar is picking up that it's going from 5 meters to 2 meters to 1 meter. Wait a second, I might beach myself. So the boat needs to then interpret that information, which is quite challenging. It's a lot more difficult than you'd think it is to program.
Okay, very nice. Chris, anything to add to that?
Yeah, I think from my perspective, there's lots of autonomous capability out there in the marketplace that we can implement. With sort of 6 to 10 hours of endurance, it would be very helpful to use that. The challenge that we're faced with, and it was mentioned earlier in one of the other conversations, is that there's a big push at the moment to move UAVs into all forms of different airspace, and not just the restricted environments that they're currently allowed in. And we work internationally across the world as well, which has its own little challenges at times. The key challenge for us is not the technology, it's not the implementation of the autonomous systems capability, it's actually making certain that the regulators and those responsible for airworthiness are happy with its implementation. So for us, not a technical challenge, it's all about legislation.
Yeah, very interesting. Certainly a different consideration. And Jeff, anything to add to that?
No, not really. We just pretty much using those waypoints for collecting our flight lines or airborne.
Okay, fair enough. Well, I think that's about all the time we have for our first Q&A session. Again, we will have time again at the end, so if you do have more questions, feel free to enter them into the system, and we will do our best to address them. We actually have a poll question, and Lori, I'll let you take care of that one.
Okay. Second poll question for today. What are your accuracy requirements for the uses that you have in mind? Is it centimeter level, decimeter level, or meter level? In this case, you can only choose one. So go ahead and let us know what you're thinking. It's 49% coming in at centimeter level, 32% at decimeter level, and 18% at meter level. Any thoughts on those results, Mark?
Seems like accuracy matters at the end of the day. Everybody wants the best possible, and I'm sure that will eventually drop to even higher accuracies as time evolves. So, yeah, lots of work to get there, and hopefully you'll see some of the benefits of being able to get there in the rest of today's presentation. The second part of our presentation is actually going to continue with Blythe, who in the first part introduced the systems, and now he's going to talk about some of the applications and the benefits of using an unmanned system for those applications. So Blythe, back to you.
Thanks, Mark. That poll question was a great segue into this next area, because often the first question people will ask, especially to a robotics company, is how can you guarantee that accuracy? How do you know that that depth is 5 meters or 2 meters or 30 centimeters? So, we can explain the technology as much as we want, but when it comes down to it, they want a side-by-side comparison. So that's what we had to do. So initially, so this is really how it works. And back in the office, you understand where you want to survey, you plan your mission, you put the system into whatever vehicle you have. This is actually my old Saturn. I've since upgraded, but the system was designed to fit into the seat of a helicopter for remote deployment. So you get to the site, you deploy it, one person, again, you launch it in the water. It has a 15-centimeter draft. So really, you don't even have to step in the water. You give it a nice shove, and it's there. You're out there collecting data. You pull it back into shore, and then back in the office, you do the post-processing. So this is the comparison study that we did. We asked a local land surveyor to go out and survey a pond with us, so we could, compare time, number of points collected, the accuracy, and basically to provide people with a better understanding of what the capabilities of the technology are, as well as the business case. So reduce cost for the end user, and for those wanting to acquire the system, we can show them just how much more they can do with this technology in their hands. So this is the stormwater pond, pretty simple, straightforward body of water that needed to be surveyed. We did the area shots side by side with the other surveyor, and then they, using hip waders or a tin boat, went out and collected about 100 points in the body of water. We followed this by putting the Kingfisher in, zooming around the forebay area. The small section at the left side took about 3 minutes. The other body of water took about 15. Overall, it was about 20 minutes for us to survey. As you can see on the left, the sonar is pinging at about 10 hertz, same as the GPS, which is really too much data for anybody looking at this and wanting to create a surface or an elevation. So we'll in-house post-process it and refine some of the points, take out some of the anomalies, and make sure that all the data points that are used are the accurate ones. So again, you can create tins and volumes of water, and this is ours at the top compared to theirs at the bottom. Again, you can see the detail in having more data points to collect from. This is the storage volume curve, so again, quite similar. There really is no ground truth unless you probably take a LiDAR image of the body without water to really understand the exact contours, but very similar. And really what it comes down to is the time savings as well. So really we're about 5 times faster for using the boat, but you know, you have the perimeter shots, the other survey points that need to be collected at the same time. So this tool is currently being used kind of as an accessory to the needs for local land surveyors. That one example was in a stormwater management pond, but we've been out in tailing storage facilities, tailing ponds for mining companies who don't want to send their crews out with rubber dinghies to ponds that are filled with nasty chemicals. Again, hydro dams, reservoirs, getting into areas close where you wouldn't want to send a diver or a manned vehicle. Shallow streams, creeks, so you know you can send a land surveyor to do these areas where you walk around, but there are going to be areas where you know it's going to be too deep. So just having that flexibility to use the system the entire way instead of you know, going from boat to waders. Coastal shoreline applications is becoming a huge area of interest, especially with increased storm frequencies and well, Hurricane Sandy and those kind of events that are really creating a lot of changes that need to be monitored in the underwater environment, as well as ports and harbors. So sedimentation that happens often, frequently, where you need to go in with dredging equipment and really understand you're getting the greatest bang for your buck with these projects, and being able to forecast as well. Okay, there's this much sediment that's accumulated, it's going to cost me about this much, so to start planning for that in the future. This is basically our first rapid prototype that we strapped together for a first survey out with Potash Corps, mining company, for potash and potassium and other things in one of their tailings facilities. And the numbers really speak for themselves. So our technician was out there for 12 hours, basically a day and a half, compared to the quote of hours which other companies were providing the consultants who we were working with. We collected 89,000 data points and really a third of the cost, with zero risk to workers. And potash, you know, their number one objective is zero harm to workers. So this kind of technology really fits well with their workflow. We did some more. We've done a lot of stormwater ponds, and this one was with AECOM, a global environmental engineering firm. What would have taken them 5 days, we were there in 12 hours. There were 17 ponds within the subdivision, and it was basically 50% of the cost, again with zero risk to workers. So there's a lot of nasty things in these ponds, obviously not as bad as tailings facilities, but you know, someone can drown with only 6 inches of water. So if you can provide a better solution that's faster, cheaper, and safer, you know, usually it's a no-brainer, and people will jump at that solution. Again, we've been in reservoirs and dams for conservation authorities where they need to understand the kind of volume of water that they have and how to release that appropriately and responsibly to maintain the type of ecosystems in the downstream environment, as well as for sedimentation and other issues like that. So, sorry, I'll go back there. Again, this is just 2 examples of tailings facilities where you collect an abundance of data, you refine it, and then you produce the contour maps and the storage curves. So we've had a lot of success with Barrick Gold, again, potash, Kirkland Lake Gold up in Northern Ontario, AECOM and AMEC, huge champions, huge supporters of the technology because it works and it's safe, and it's a win-win-win really for their clients, the data and their ability to use the data to provide meaningful information and to make sure everybody gets home safe at the end of the day. So I guess call to action is be safe, use robots, and with that I'll pass it back to Mark.
Great, thanks a lot, Blythe. Again, very interesting. I think the applications there are really eye-opening, and certainly the benefits are impressive. Our final speaker, panelist, will be Chris Day. And Chris, since 2012, has been the head of capability engineering at Schiebel, which is a global provider of unmanned helicopter systems for a diverse range of customers. And in that role, he leads the global capability development for unmanned systems. He joined the company after a 30-year career in unmanned system research and development for the UK Ministry of Defence, and more recently in the role of Vice President of ISTAR Systems at Thales, where he led the organization with responsibility for ISTAR system development across international defense aerospace markets. He is the director of Bristol Unmanned Systems Conference, the world's longest running conference dedicated to unmanned aerial systems technology. He began his professional career as an avionics engineer with the Royal Aircraft Establishment, and he has a bachelor's degree in earth science and a postgrad qualification in computer and microprocessor-based systems. And Chris is going to talk to us about some of his experiences from the field and the considerations that you should be aware of when designing your own system. So Chris, take it away.
Thank you very much. And once again, I'd like to extend my thanks to the organisers for giving me the chance to speak. And also a special thanks for the people that have been organising the webinar itself, because without them, it would not be taking place today. It has been a great experience. I just thought I would give you a quick overview of the Schiebel system as it's presented here. It is difficult to get an appreciation of its size. And its weight. So that's a complete system that you can see in front of you on the slide. It's about 3 meters from one end to the other, weighs a couple of hundred kilograms, and in reality, it's been specifically designed to perform a lot of the surveillance type functions that you'd expect of a conventional manned aircraft. It'll fly generally on a regular day out to a couple of hundred kilometers. And as I said earlier, it'll quite happily do that for between 6 and 10 hours, depending on how we configure the fuel for it. You'll see the 2 laptops on the bottom there. One is basically for waypoint planning. So it's almost, it's automatic with a little bit of autonomy in there. Doesn't take any piloting skills. It just goes basically where you tell it to on a map. And the other computer there is basically for the different types of payloads we carry. And when this helicopter was first built about 10 years ago, it was primarily aimed at the sort of surveillance market, which I think most people are familiar with. And at that time, its key sensor was a video camera with a combined nighttime thermal imager as well. So it had the ability to capture imagery both day and night. Since then, certainly in the last 3 or 4 years, the market has changed quite a lot, and part of my role is to, as I call, future-proof it, and that is to look to new markets, look to new customer requirements, and we started to get a lot of interest in agriculture, in mining, and in some other non-military, non-security type applications, and I'll come onto those in a minute. You might be able to see that back on the tail fin, right at the very end, we mount GPS antennas, because historically with the rotor blades flowing around at a few hundred RPM, they were having an effect on the accuracy of the GPS, and I'll explain in a minute why we need particularly high quality GPS INS combinations. So it has been a problem for us in the past, and one of the reasons is, although we have carbon fiber rotor blades, we have a leading edge that is nickel plated, so part of it's metal, part of it's carbon, but it effectively acts as a fantastic modulator of the signal, unless we get GPS antennas out of the way. Today, it is operational on 3 oceans, and what does that really mean? It means that we can not only be reliant on standard GPS, we have to look for other solutions as well. We operate in cold environments, mountain environments, desert rainforests, and every one of those changes the impact on the air vehicle, the way it responds. It impacts some of the challenges in terms of the accuracy, the requirements we want. And the big challenge for us, and it really is I suppose, the toughest thing. It goes back to the question earlier, what level of accuracy do we need? Well, we certainly need centimetric, and there's no getting around it. That helicopter, 3 meters in length, will automatically recover to the back of a ship's deck, which can be no more than sort of 8 meters square. In quite high winds, we've done it up to sort of 30 plus knots, and we're also doing with a deck that's really moving about. We refer to it as sea state 5, which means it's really kicking around. It's something that you certainly want to be stood out there for very long without feeling it. So from our perspective, we need a GPS INS system that allows us to not only control the air vehicle, but we put a system on the aircraft, on the ship, sorry, and the information from that GPS INS combination is fed up to the aircraft, and the aircraft can then start to monitor and measure the ship's movement and then start to replicate it. And when it understands that and it's got a high level of confidence that it understands the ship's motion, it can then take the necessary maneuvers to land it on the back of the ship. And we do that now pretty much automatically, have done for some time. But what that really means is, because we are relying on that, is we need a duplex navigation system. And like every unmanned aircraft system, it needs to be lightweight, it needs to take as little power as possible, and it needs to be reliable, because there's no doubt about it, helicopters are not in terms of vibration and shock loads and various, they're not the best platforms for hardware. So we need a tough system, reliable system. We go for a duplex. And one of the reasons that's really important for us in terms of high accuracy navigation is there's a number of sensors there, and predominantly a couple of them are radars, and they can see a long way. They can see 30, 40 plus kilometers. And the key measure of those is not only do we want to see 30 or 40 kilometers, but we want to be able to accurately geo-register anything we see at those distances. And in order to do that, we need high accuracy INS GPS. There's no way around it. It's got to be as high as we can get it. And on some of the very latest radars, we need to know the aircraft position to within millimeters at times. And the further we are from millimeter accuracy, the further, or the poorer the imagery, the poorer the geolocation accuracy. And today, there are customers out there that want to know the position of targets or the position of objects of interest, moving vehicles. When you're looking at them from 20 odd kilometers away, they want to know that accuracy is perhaps down to 25 or 30 meters. So from our perspective, we really do need to have systems that are highly reliable and give us the ability to produce these amazingly accurate geolocation accuracies. The other challenge that we've started to experience, and something that worries us quite a lot in the unmanned systems world, is that GPS is starting to have, there's areas of the world where GPS denial is starting to become an ever more problem. It's becoming more and more frequent, and it's becoming more and more difficult to predict. And there is, I suppose, most of the unmanned systems market up to this point in time has grown around the reliance on GPS, and all of a sudden that foundation on which most small unmanned systems have developed is starting to get quite shaky and quite an area of concern. So certainly for a lot of our customers, with something this big, where the sensors are hundreds of thousands of dollars, some level of resilience is now essential. It is unacceptable to sort of put a system up in the air that cannot survive should GPS go down. And that becomes even more critical when we look at point recovery on the back of a ship. Because if you lose your GPS at that point and you're trying to recover to a very, very small spot, then it all becomes a bit too difficult and a bit too demanding. So very recently, we put a new system, or we've got a system available that goes on the back of the ship that effectively turns the GPS capability upside down, in that we put pseudo GPS satellites around the back of the deck, and we squirt those informations up to the aircraft, and then we can actually do a very accurate centimetric view accuracy recovery to the back of ships in the GPS denied environment, and that's kept some of the concerns about GPS at bay for a while. I'm sure it's coming. The other thing is we are an international, worldwide company, and we have systems deployed pretty much all over the world. for both security companies, for mining companies, for oil and gas, and for various others. And the other challenge for us really is that with the proliferation of global positioning systems in terms of Galileo, GPS, GLONASS, every country now is starting to want a different combination. If not a different combination, they certainly want their own system. But generally, the ask is always about, can we have a different combination? And that is, from a technical perspective, it's not especially difficult, but it's just another complexity that we have to consider when we're looking at all the other challenges associated with implementing it, getting the accuracies out, getting the reliability. And more specifically for us, because it is designed to fly in every aerospace environment, is, we've got to be able to maintain the airworthiness. And that's a cost and a complexity that certainly remains a challenge. The helicopter that you can see in front of it with the boxes on at the moment, that is our first real push into a UAV that is specifically designed for the navies of the world. And that is a triple sensor helicopter that carries little radar. It carries the ability to detect radar emissions. And those radar emissions can be tens and tens of nautical miles away. And once again, it's really important that we have highly accurate GPS, INS combinations in order to make certain that when we are making these detections of tens and tens of nautical miles away, that we get their accuracy as good as we can. Certainly, the little radar on the side there is something that creates a synthetic picture of the ground. So all weathers, day, night, doesn't matter what the weather's doing, we can get a really good, high-quality image of the ground surface and things that are going on the ground surface. But that is totally, the quality of the image is totally dependent on the quality of the INS and the GPS. And as a consequence of that, we're beginning to find that a lot of these high-tech sensors now, the manufacturers are actually delivering the sensors with their own INS GPS units on board. The INS is not a problem. GPS means that we normally have to put something at the end of the tail, and the poor old tail is starting to look like an antenna farm. And it's something that we're going to have to address at some point in the future. But basically, a lot of these sensors have their own individual INSs and GPS, and that way we can actually guarantee the accuracies out at some distance. I mentioned earlier that at the end of the day, it is 100 different vibrations all focused in one particular mechanical area. And as a consequence of that, and it is a function of most large aircraft anyway, you will find that where the sensors are and where the INS are, they might be several meters apart. And as a consequence of that, even that change and the vibration and the shocks and all the things that are going on can lead to some quite interesting heading or quite interesting attitude or quite interesting position errors. And every one of those contributes to a degradation in the location accuracy that we're trying to achieve. So putting a separate INS GPS onto the sensor allows us to address some of those problems and maintain that accuracy, which is absolutely critical. I mentioned a few minutes ago that denial of service is becoming ever more of a frequent problem. We've had it now pretty much everywhere, both in Europe and overseas. It is becoming a serious concern. It's something that I think the unmanned systems community is going to have to look at ever more carefully. There are techniques around, and there have been unmanned aircraft certainly that have flown without a need for GPS, and we can use data links to help us to a certain extent. The challenge with that is all the other alternatives don't allow us to deliver those accuracies in terms of target or in terms of location accuracies we need from the sensors. And we see a degradation in that. So there's got to be a fusion that takes place in the future years. The problem is it is becoming unpredictable. We can't tell when it's going to happen. In some circumstances, that's deliberately so. And we talk about it as a capability level. It's something that you can do quite quickly. As a threat, it's readily available in certain parts of the marketplace. And literally it has such a significant effect that it is starting to be a significant concern for many, many communities. And then, of course, when we try and talk about pushing this technology into the wonderful world of the rest of manned aviation, if we start to lose GPS and we start to not particularly know exactly where that aircraft is, it starts to become more of a concern. and raises another shed load of issues. I think unless we find a ways around it, and I know there's a lot of good people doing a lot of great work in this area, unless we can get over this challenge and we can get over it in the near term, then it is going to be a significant threat to the growth of our manned systems. Because at the end of the day, there's not a man on board to take over when the GPS goes down. Systems heavily reliant on that navigation accuracy, albeit there are other ways and techniques of getting around it. But we must remain, as I say, cognizant of the fact that it does have the full potential to impact its future growth. Today, in terms of things for the future, we've been looking at, and sensors we've been looking at, we've flown LiDARs, all sorts of different LiDARs with bathymetric capability in all parts of the world. We've got some fascinating results. We currently fly a hyperspectral, which allows us to identify minerals out of the from an airborne perspective, so we can map mines and we can map open cast mines quite quickly and quite accurately. And if we combine it with a LiDAR, as the previous presenter said, we can not only get a great 3D image of the ground we're flying over, but we can then start to identify on that LiDAR map or that point cloud map and start to identify some of the minerals that we're detecting. Talked about the radars and the ability to see huge distances in maritime and land environments. And of course, there's the electro-optics that allows us to do the surveillance type task. And they're getting ever more capable, ever more stable, so that we can see even further. And the image quality with high definition coming around is massive and huge. Very recently, we also started to talk about magnetics and gravimetrics. So we can put a boom out the front of the aircraft that allows us to support the mining and the resource investigation community, and then in order to help them find the best places to look for some of the much needed resources around the world. So from our perspective, it is pretty much focused on taking on the manned helicopter world, but doing it a lot more cost effectively. And I say one of the key things is that we can last for 6 to 10 hours. We can fly a couple of 100 kilometers. If the pilot gets a little tired, we just move the laptop to the guy sat next to him, and that's as tough as it becomes. So for us, it's it's a great opportunity. Lots and lots of interest in it out there today, but the big challenge is we've got to get back to a point where we get some form of resilience into the combined GPS INS systems. And with that, I'd like to thank everybody again, and I'll pass back over.
Great, thanks a lot, Chris. Again, another wonderful presentation about some of the really interesting applications with unmanned systems. Before we get to the poll question and Q&A, just a bit of information for you. The PDF presentations as well as the actual live recordings will be available on the Inside GNSS website, so insidegnss.com/webinars. We have the contact information for our sponsor, Novotel, as well as for our 3 panelists, and you're obviously welcome to follow up with them if there's specific questions you would like to have addressed, if we don't do that either via the Q&A or in the days that follow. Before the Q&A session, I'll turn it back over to Laurie for our last poll question. Laurie.
Okay, thank you, Mark. And folks, we have that third question on the screen. Again, asking on your honor system if you would select your top 2 choices. What are the limitations to adopting an unmanned system from your perspective? Is it cost or return on investment, learning curve, familiarity with technology, regulatory concerns, or data accuracy? 42% saying cost, return on investment, 13% learning curve, 30% familiarity with technology, 72% regulatory concerns, and 30% data accuracy. Any surprises here, Mark?
Yes and no. I mean, obviously, there's a lot of technical challenges out there, but it seems that the main concerns really revolve around meeting the regulatory issues, as Chris mentioned in the last Q&A. So, although the technical challenges are still there, there's still many other obstacles that people need to be aware of. I think that wraps up our final poll, and now we will get to our Ask the Expert section again. So again, please feel free to enter questions as you go. We have several lined up here, so we'll try our best to get to them. The first question I'll ask to Jeff, and Chris, you may want to chime in afterwards. There's been several people who have asked about how good GPS or GNSS receivers operate underneath rotors of helicopters. I was wondering if you'd be able to comment on that.
Okay, that's a really good question, and that was a big concern of ours when we first started going with an airborne solution. Because I know that the vibration, there's a lot of things that play in. So it's not just the blades, but so far, in our experience, we found, because we do post-process solutions, so we keep a base station relatively close by, which helps us, but in Inertial Explorer, which is from Novatel, we use that. We can see if the data coming in is being chopped up by the by the rotors. We can see if it's cyclical or not, if there's a pattern to it, and we can put that in as a parameter, and we can solve for that. Help the solution come to a better answer based on that. But so far, we really haven't had an issue with it. We know that the capability exists. We try to pick the appropriate INS system that works. We always try to have a really good antenna, so we don't go for the little teeny antenna generally. We have a full-fledged, highly accurate system, but we do watch for that. We just haven't seen it yet.
Very good. Thanks, Jeff. Chris, anything to add to that from your experience?
Yeah, certainly we've had a problem with it. There's no doubt about it. We're quite a compact system, and the choices that we have available for mounting GPS antenna are few. And in the early days, we certainly, with the carbon fiber blades, we certainly had a few challenges. So as I said earlier, today we mount them on the tailplane, which is out of the influence of the rotor blades. So yeah, we've had problems. I know others have had problems, and we tend to do our best to make certain that the antennas for the GPS in particular are outside of the influence of the rotor blades.
Okay, you're coming in a bit low there. Perhaps speak up next time. But does that ultimately affect your end accuracy of your system? Yeah,
certainly from our perspective, it causes a few problems, and yeah, it's another unpredictable issue that we don't want, because the challenge for us is the regulation world, and unpredictability and regulation never work well. So yeah, from our perspective, it's a problem we can live without. So by putting them on the tailplane there, out of the way, we can get over the challenge.
Very good. Great. Thanks a lot. Much clearer there, too. Blythe, the next question is for you. You generated a whole string of questions, so we'll try and get to them as best we can. The first one is about timing, which was actually discussed quite extensively on Wednesday. The question is, do you trigger GNSS and sonar at a certain distance or time interval, or do you somehow do some time matching after the fact in post-mission?
Sorry, yeah, we do some, we match and interpolate. So we're using industry standard hydrographic software, and a lot of this is done with that software, so it's a pretty straightforward process.
Okay, and is there a particular timing accuracy you require?
Really, no, we're trying to do things as continuous as possible. So, no, there's no no timing.
Okay, fair enough. That's all right. Next question is to you, Chris. This question comes from Logan. He was asking about specific examples of GPS outage that you have seen.
Yeah, I've been lucky or unfortunate, whichever you want to pretty much deploy UAVs to most hotspots around the world, as well as I say, commercially. I've seen them all, basically, all the types that you can imagine, but the key ones is the standard jammer that just denies the signal, and then there are the smarter, cleverer ones which have the ability to locally to spoof the air vehicle into thinking it's somewhere else. So yeah, both are readily available, and both are being deployed today.
Okay, very good. Jeff, the next question is for you. Again, we've had a few people ask similar types of questions. We know that it's possible to merge the LiDAR with the GPS and inertial in order to get a better positioning accuracy. Have you found that necessary in your applications, or do you perhaps foresee that might become important for you down the road?
Say that one more time. To merge the data, you say?
Yeah, so there's opportunities to combine the LiDAR and sonar information in order to improve the GPS and inertial navigation performance, particularly in degraded areas. Have you come across that as an issue?
We have not actually. No, we actually haven't ever had that happen.
No? Okay. Chris, have you seen anything or any thoughts along those lines for your applications?
No, not really. It's a point that I'm not that familiar with, that we've had a lot of experience.
Okay, I think that perhaps the takeaway then is that you know, the GPS inertial, at least for the application you guys have been dealing with, is generally sufficient for meeting your accuracy requirements. Is that a reasonable statement?
Yeah, we pay big bucks for ours.
Yep.
In order to make it happen. So it should be less of a problem for us.
Okay.
I agree.
Okay, great. Next question, Blythe, was to you. I'm just trying to find it here. There's a whole bunch of them here. Oh, yeah. Could your boat be used for mounting other systems, for example, a LiDAR, and the example application would be for stream bank erosion or vegetation detection?
The short answer to that is yes. We've actually been investigating the feasibility of that. It's been requested multiple times, and so that's what's triggered us to kind of go in this direction. We won't build anything unless somebody's asking for it. So we are looking at this. It is possible. Again, it will take, with LiDAR, for obviously we'll need an INS system, and those are quite expensive. So, you know, that poll question about business case, ROI, we have to know that there's enough work out there to pay this off. But if a customer is asking for this solution, then the answer is a definite yes, it can be done.
Okay, very good. Next question I will throw to Chris, but I'll ask kind of everybody else to chime in after that. The question comes from Antoine, and I'm going to paraphrase it a little bit. He's asking about how RTK and DGPS systems can be expensive in lower cost systems, such as small unmanned systems. Have you found that the cost of these products is prohibitive? And perhaps I might ask that in the context of dual frequency versus single frequency receivers.
Our market point is very different, I suspect, to a lot of the small UAVs. So from our perspective, in reality, that they're not inexpensive. I mean, I come from 30 years of research where, when GPS and IS wasn't around, the amount of hardware you needed to replace that function was quite extraordinary. It's easier to do it today, but it's still, you know, it's still an expensive activity. So for what it performs and the function it provides and the quality it provides, when you put it in the overall picture, it is relatively cheap. But in financial terms, for small UAVs doing, you know, a different type of task, I acknowledge and accept that, you know, it's not the cheapest part of a UAV. But as I say, from our perspective, when we're dealing with sensors that cost hundreds of thousands of dollars, it's a small contribution to the overall system cost.
Okay, fair enough. Jeff, your thoughts on that one?
Yeah, I mean, definitely the INS system is for us, it's a pretty big factor because the clients want to have the best results at the cheapest price in the smallest size, and to achieve all of that, you know, especially to make it more and more accurate and be smaller, makes the price go up, obviously. But everything's been just naturally condensing, smaller and cheaper both. So we've been pleasantly surprised, actually, just in the last year, how things have changed. It's been quite a change. Now, for a lot of UAV guys that think of an expensive INS as $500 or $1,500, yeah, they're in for a shocker when they get it. It's $25 or $50 or $150. But for most of the mobile mappers, you know, if your system costs $1 million and your INS is $150, okay, 10%, you know, we can live with that.
Fair enough. Fair enough. And Blythe, to you, any comments on the cost of your GPS and in the overall system?
Well, when people are looking for RTK solutions and they want to have a GPS solution that they can use for land survey applications as well, that system almost doubles the cost of compared to just the vessel itself. Yeah, when looking at dual antennas, you're looking for the complete solution, and therefore the price skyrockets. So, yeah, it's a big issue. But again, the prices are coming down significantly, and size and just the feasibility to integrate all this onto an unmanned system such as ours, which is quite small, is looking more and more. It's looking positive. So it does make a big factor.
Okay, very good. And just as a quick follow to that, Blythe, single frequency or dual frequency systems that you use?
Single frequency.
Okay, Jeff?
Almost exclusively dual frequency.
Okay, and Chris? Dual frequency. Okay, very good.
Yeah.
All right, Chris, the next question is to you. What is the cost of a reasonable LiDAR grade UAV?
Oh, good question. It's great because it goes back, I suppose, to Jeff's challenge in his life. Jeff is producing ever smaller LiDARs, and that's really important because it's been the payload at the end of the day that drives the size of the air vehicle. We've recently flown a very, very high quality bathymetric LiDAR to do some quite outstanding work in a coastal environment. And that sensor's costing hundreds of thousands of dollars. And as a consequence of that, you're not going to bolt such a LiDAR on a relatively small platform. It has to be something that's reliable, and it has to be something that that you've got confidence that it's going to do the job in. So those sort of UAVs are coming on in at $1 million plus. But then, as I say, with the work that Jeff's been doing and other manufacturers in Europe have been doing, LiDARs are getting ever smaller, and there's no doubt about it. You can do a fantastic job, as Jeff's clearly explained, using some quite simple unmanned helicopters or unmanned fixed-wing aircraft for that are just a few $1,000s. So the market's quite broad, depending on the real requirement of what the customer needs you to do.
Okay, fair enough. Jeff, anything to add to that?
Just a little. I mean, I have no problem putting my let's say $150,000 or $200,000 instrument on a $5,000 or even a $1,500 rent-a-wreck car, but I don't think I'd put it on a $5,000 UAV.
Fair enough. Fair enough.
I want a little more reliability, a little more durability. I want it coming back.
Yeah,
sure. Understandable, I think. Next question to you, Blythe. Obviously, we've talked about the role of accuracy and the ability to ensure you get that. There's a question here from Michael asking whether or not you think, in your opinion, whether it's necessary to have a certification of your system done in advance, much like you did with the surveyor that you had called in for your system.
So we did that comparison because we just wanted to basically set the standard, let everybody know that we have done a test like this, and it wasn't just throwing sensors together and saying, hey, we have a solution. So that was kind of a one-off. However, doing work with clients that are already there, they'll often go in and double check things as well. A lot of the engineers, for their own confidence, just want to make sure that the accuracy is there. So this comparison test isn't done all the time, but when requested, I guess.
Very good. And the last question I'll actually put out to everybody, maybe I'll start with you, Jeff. In your application, are you more concerned with positioning accuracy or attitude accuracy or both?
That would be both. I mean, if we know where we're at and we don't know where we're looking, we're lost.
Fair enough. Chris?
Yeah, absolutely. We need orientation, position, and attitude. We need them all to the highest possible accuracy.
Very good. And Blythe, last one to you.
Yeah, well, I'll say both as well. And actually, I wanted to correct myself earlier on the previous question with single or dual frequency. It's also dual. I was thinking in terms of the sonars we've used, and asked that question as well for single beam, multi-beam, dual frequency. So I had my mind in the wrong place. Sorry about that.
No worries, no worries. Very good. So that about wraps it up for the Q&A, or the time we have for a Q&A. So if we didn't get to your questions live, we will endeavor to do that in the next several days and get back to you in writing. And with that, I would like to thank everyone for participating, including the panelists and the attendees. And I'll throw it back to Lori to wrap it up. Lori.
Thank you, Mark. And folks, before we sign off, I would like to say thank you to all of you for joining us. Trust that you found today to be of value. Special thanks to our moderator for today, Mark Petavello. Fabulous job. And speakers Jeff Fagerman, Blythe Gill, and Chris Day, spanning around the world today and multiple weather patterns as well. Of course, our sponsor and co-host, Novotel and Inside GNSS. Would like to thank our logistics producer, Patty Van Hooser, for her behind-the-scenes collaboration and support as well. Whether you joined us for 1, 2, or 3 of the sessions that made up Unmanned Systems Week, thank you for tuning in and have a great rest of the week or a great weekend. Bye for now.